And I'll be talking about my summary of the virtual core flow cytometer. So flow cytometry is a cell analysis technique that is used to measure the volume of cells in a rapidly flowing fluid stream as they pass in front of a viewing aperture. It was developed in the 1950s, and after many improvements over time, it is now capable of achieving rates of over 10,000 cells per second and over 30 detectable fluorescent parameters. Although it allows for rapid analysis and statistical power, it comes at the cost of being unable to detect morphological characteristics in subcellular localization common to microscopy. Some applications for this technology include detection and measurement of protein expression, RNA, cell cycle status, cell health, and even identification and characterization of distinct subsets of cells within a heterogeneous sample. So to define the problem from the paper, they look at the fact that a flow cytometer must consistently position the particles with respect to the focused laser beam in order to accurately and precisely measure presence and quantity of fluorescent molecules. This can be accomplished via hydrodynamic focusing, dielectrophoretic focusing, capillaries, and acoustic focusing, and also requires the use of a sheath fluid, which is the fluid that carries the cells throughout the cytometer. In the first image, we can see an example of one of the focusing measurements, which is hydrodynamic. This is where a sample is injected into a stream of sheath fluid within the flow chamber, and they are forced into the center of the stream, forming a single file by the principle of hydrodynamic focusing. This allows for the cells to be pushed over the center of the aperture to give the best readings. So this works by having the cells being counted to be streamed into the flow cytometer and the sheath fluid used to essentially drive the cells into the center of the cytometer, like I said. The problem arises here in that several liters of sheath fluid are needed every day, and attempts to use either filtered, readily available fluids or recycled sheath fluid have not been successful. So it's critical to try to find an alternative to get the same kind of reproducibility and quantification, but without needing all those liters of sheath fluid. So this paper attempts to address this issue through developing their virtual core flow cytometer, or VCFC, with the ability to detect the position of cells without the use of a sheath fluid. This is their solution to needing sheath fluid in a flow cytometer by developing their virtual core flow cytometer free of needing that sheath fluid, like I said. To combat this need, their system utilizes a combination of photodetectors that can sense the position of the particles. These photodetectors, in combination with mirrors and photomultipliers, allow for the detection of particles that are properly positioned. Those that do not pass directly through the focal region of the optical system will be ignored. This way, they only use the measurements that are found from the particles that are passing over the center so that they don't receive poor measurements from the non-centered particles. This is seen in the figures here. In the figure on the right, it shows the different stages of the VCFC, that the VCFC can be in. In A, you have the focal plane, or the light just hitting the focal center point. In B, you have it offset so it hits one of the orthogonal detectors, and in C, it hits all of them. So in A and C, although in C it hits the orthogonal ones, since they both hit the center point, then those can receive good measurements. In B, however, you see that it's slightly offset so that it only hits the mirror and bounces the light to the orthogonal detector, showing that it won't actually pick up any of the particles in the center, if there are any. Showing some characteristics from confocal microscopy and quoting the paper, the system is based on the principle that light from a properly focused object will pass through a pinhole located in the image plane, whereas improperly focused images will cast light onto multiple detectors located at the edge of the pinhole. This is to ensure that they only receive measurements coming from centered particles so that they can get the best possible measurements. To test the efficacy of the PSD, they looked at the sensitivity of this device versus a traditional sample and sheath fluid cytometer. Based on the figures from the test, they saw that the PSD detector can be used as the heart of the VCFC that is able to sense the position of particles which have a similar size to those suitable for the traditional sheath fluid-based cytometers. Additionally, the PSD can be refined through using different shapes of the pinhole for the aperture rather than the rectangular aperture. Altering this pinhole shape will change the amount of light sent to the orthogonal detectors, leading to different amounts of detection. Another evaluation was done in which its ability to perform immunophenotyping and measure phytoplankton was tested. They compared it to a traditional cytometer by allowing the system to switch between the virtual core system and a fluid-based system. Results, as seen in Figure 2, compare the evaluation of bivariate plots of CD4 and CD8 expression in marine thermocytes. Comparing the sheath fluid system to the virtual core after the gating to determine the virtual core is applied seems to be similar in results. In fact, it is less than 2% off the traditional cytometer results. That's a good sign showing that it's pretty accurate in comparing the two the traditional one to the new virtual core. However, there seems to be a loss in data for the gated measurements. Just visually, you can see that comparing C to A, there's way less data points in C. And according to the paper, there were only about 1.4% of the cells from B that were centered appropriately and therefore only able to be used. So while they can match the quantitative results, they lose out on the amount of data obtained compared to the traditional. So in conclusion, from their work, this group developed a virtual core cytometer that could achieve similar results to a traditional cytometer without the need for supplying a large quantity of sheath fluid. It is also less complex and allows for greater use in field laboratories in those areas in which traditional cytometer is unrealistic to use. One example from the paper they said that they discussed was that it can be used to measure phytoplankton populations from ships, whereas the use of traditional cytometers would not allow this to be done. Future directions include more complex quantitation of marine groups through image-based analysis of internal standards to allow for environmental concentrations to be taken. And the removal of sheath fluid also allows for the complete characterization of samples. Since there's a large amount of sheath fluid in traditional cytometers, it dilutes the sample by up to 100-fold with each successive analysis, which makes characterization difficult. The little amount of sheath fluid needed here and the fact that it is only needed in the first measurement means that the VCFC can measure the sample multiple times without worrying about dilution. In conclusion, the work presented here seems to hold up against a traditional flow cytometer, and while not perfectly matching results from a traditional cytometer, the virtual core obtained results within 2%, but still has room for refinement and advancement. It allows for greater and more diverse use in the field and opens up greater possibilities in the future. Thank you.